Good afternoon, everybody. So today I'm going to tell you about some recent work that I've done with my colleagues Valerie Sahakian and Amanda Thomas and graduate student David Small. And I'm a seismologist, so I'm not really a geologist. So it's difficult for people like me to get into this word paleoseismology, but we do our best. So if you fall asleep today and take nothing else away from this lecture, it is this. I'm going to tell you that, as many of you know, there have been no great earthquakes in the Cascadia subduction zone in instrumental times. Instrumental times in seismology basically means the last 110, 120 years or so since we have seismometers. And that the most recent event, large event, very large event, something like a magnitude 9, like what is shown here, a wall-to-wall or full plate boundary rupture from Vancouver Island to the Triple Junction in Northern California, that the most recent event was likely on January 26th of 1700. This is well-established lore of the Cascadia subduction zone, nothing new there. And that there are paleoseismic proxies that provide the constraints on this earthquake history for our region. From this, two important conclusions have been drawn. And this is where we get into the meat of the matter. First, that the 1700 earthquake, that event on January 26th of 1700, was indeed this full plate boundary event. And I'm going to spend 97% of the talk talking about A, because it's really important. The second conclusion that has been drawn is that big events like this one, big magnitude 9s in the Cascadia subduction zone, they don't rupture inland of the coast. And what we mean by that is, if you look at the slip, this is a model, this is not the earthquake itself, but the colors here denote how much slip is happening on the plate boundary. If you look at it in cutaway section down here, so this purple would mean that there's about 20 meters of slip right here at the plate boundary during that particular rupture. These sort of pinkish colors would say 12-ish meters of slip further down. So the established geophysical story for Cascadia is that during these big events, rupture goes from the trench roughly to below the coast and never further down, or more than likely never further down. So those two things are very commonly told about the Cascadia subduction zone and big events. And what I'm going to discuss is improvements in modeling of large earthquakes, and I'll systematically test what kinds of earthquakes and what kinds of ruptures match these paleoseismic proxies, the evidence of past big events. And I'll walk you through what a paleoseismic proxy is here in a second. And so I'm going to conclude that those two things, A and B, are still totally possible. I'm not changing or rewriting what we think we know about Cascadia, but they're not proved beyond a reasonable doubt. So if you want to use terminology from a court of law, what I will argue is that alternative hypotheses are still just as likely as what has been established as the dogma for the Cascadia subduction zone. The first one, that the 1700 event could in fact be not one event, but many, spanning years to decades. The geology allows that, and so does the geophysical modeling. And B2, that ruptures can indeed penetrate far inland, like for example, this one, where the slip, I'm sorry about the change in color maps. This bugs me every time I give my own talk. But that the slip goes, here's the coastline. The slip can in fact come well below the Willamette Valley. I live right there. We're somewhere over here right now. And so rupture can indeed penetrate far inland and still respect the geology itself. And I'll talk very, very briefly about the second one. I'll just show you what the implications are if that's true, for what the shaking would be like in the Cascadia subduction zone. Why do you care about this, or why should you pay attention for the next 40 or so minutes? If you like basic science, then this is an interesting thing to know about our subduction zone. Understanding the geodynamics, tectonics, and rupture dynamics of big earthquakes is critical to understanding the long-term earthquake cycle behavior of our subduction zone. How does it behave over many, many earthquakes? And so whether it's full plate boundary events or sequences of ruptures, whether rupture is shallow or deep, colors what we think we know about basic science processes in Cascadia. If you are the kind of person that cares about applied science, well, then this is a first order input. If you ever want to make a seismic hazard map of the Cascadia subduction zone. Knowing how deep the rupture goes, knowing whether it's one or many, is what leads to the map looking orange or red or purple in places where it looks orange or red or purple. So these are first order things we really should figure out, so that when we produce maps like this that we show to the public or that we give to agencies or decision makers, so that we know that the best science and the most accurate science went into making maps like that. Remember that hazard maps like this, they look very precise. They look like we know exactly what's going to happen in big earthquakes, but they never are. They always reflect the best state of knowledge at the time that a group of scientists got together to make the map. So everything in this talk today revolves around paleoseismic proxies. A paleoseismic proxy is a geological clue, something in the landscape that we can attribute to a past earthquake. It's not the earthquake itself. It's not the fault itself. It's not like you can put your finger on an event like you can maybe in a trench for a crustal fault. It's the indirect effect of a rupture left behind as evidence. And so a couple of examples. This is the type location for the most famous kind of paleoseismic proxy in the Cascadia subduction zone. This is southern, well, central-ish, southern-ish Washington. This is Willapa Bay. And right here is the Goose Point Oyster Bay Company. You can park just across the road and amble down to these tidal flats. This is a tidal stream shown here at low tide. You can see this tidal mud. At high tide, this would be covered. And so this picture is taken right here in the Neowayakam tidal estuary. So if you amble down from the road there on the right-hand side down into these tidal flats, and after you clean out a little bit of that scarp, well, of that outcrop, what you're left behind is something that looks like this. This is a tidal marsh. So you can stand up here. You can see these tufts of grass. There's actual modern-day marsh up here. You can stand there and look down onto the tidal stream. And after it's been cleared out, you'll see very clearly this organic rich horizon, this paleosol, essentially, right there, maybe, 5-ish feet below the present day marsh. And the idea is that what you're looking at here is evidence of co-seismic subsidence. This used to be the marsh. This used to look like what it's like up here, but during a big event, a big magnitude 9, presumably, the land drops something like 1.5 meters or 2 meters. And after the land drops, because this is in a tidal estuary, this now is at the tidal, intertidal level or maybe even below. And so the buried soil is progressively covered by muddy deposits that are left behind every time the tide comes in and goes out, comes in and goes out. And so here you can actually see many sequences of this. You can keep digging down and you can find repeated subsidence events. Now, this is everywhere across the margin. The other thing you will notice here is that right above that organic rich horizon right there, there's this sequence of very obvious sandy layers that I've outlined here for you in purple. There's also actually one right there at the contact that's hard to see. But if you can actually trace it over here. But if you're right there, you can pick it up. And the idea is that right below this, right after subsidence happens, which in an event happens in the first minute, 2 minutes after the rupture, the tsunami, maybe in Willapa Bay, you're probably talking about maybe 45 minutes to an hour after the earthquake. The tsunami comes on shore, like in this sketch cartoon, marsh subsides, tsunami comes on shore and leaves behind these sandy deposits. Interesting to think about whether we could use the pattern of these deposits, the fact that we have 4, one thin, one thin, one thick, one thin, and so on, whether we could use those in more advanced modeling to say something more educated about the tsunami. That's something I think about all the time, but I have no answers for you there. The point is that there's evidence of paleosubsidence and evidence of a tsunami. That's not the earthquake itself. It's evidence that something really big, cataclysmic even, happened in the past. And so those are the two most common kinds of paleoseismic proxies in Cascadia, the subsidence or the land level change, and evidence of tsunamis. There's others. Those of you that are familiar with the story of the Cascadia subduction zone know about the turbidites, offshore landslides, essentially, triggered in these deep water canyons and sometimes at the toe here that leave behind deposits that people have cored over and over and over again I'm not going to talk about them today. I can if you want to, but you have to ask me a question at the end, and I'll tell you everything I think about the turbidites. But they're just more difficult. They're actually right now, they're near impossible to model. So I'm right now going to focus on C and D, which are the things we can model really well, and see what kinds of ruptures align with those two. So evidence of coseismic subsidence, this land dropping at the coastal marshes, exists in a lot of places up and down the subduction zone. So here, every point where you have a circle in green is somewhere, and this triangle in green is somewhere where people have measured this paleoseismic subsidence. And the values here show you what we think are the ranges of subsidence at those sites. So at this Vancouver Island site here, we think that coastal subsidence was 70-ish centimeters, plus or minus 20 centimeters or so. In other places, like maybe, this is Willapa Bay actually, I think. Here the subsidence was more like maybe 1.3, 1.4 meters, plus or minus almost half a meter. But the point is that the subsidence is everywhere. We don't really see uplift, we see subsidence. The coast seems to always be dropping during these very big events. Now, how we estimate the subsidence is itself a really interesting story, one that I'm fascinated by as a total novice to micropaleontology. But the way you estimate the subsidence is by actually counting the kinds of microfossils that you find in sediment cores. So a paleoseismologist will go to a marsh, punch a core through the old marsh floor and into this old soil. And by looking at how the relative abundances of microfossils change, mostly forams, but people also look at diatoms these days, you can actually back out a numerical estimate of how much relative sea level, and thus how much the land must have dropped during that event. Fascinating stuff to think about. I know nothing about it. You should bring a micropaleontologist from the climate change or paleoseismic communities to tell you about this. It's really interesting. But anyway, we're going to take them at their word that you can do that and that you can produce these numerical estimates of subsidence. As a modeler, I'm just going to assume that that's data that I can compare models against. The tsunami deposits are also everywhere across the margin. At every site where you see a red dot over there, at least a single core has been identified with a tsunami deposit. And at some sites, people are starting to do really creative things, like actually trying to map the 3D distribution of the tsunami deposit. Shown here is the Salmon River site in Central Oregon. And each one of these circles, both white and purple, is a core that somebody has punched again through the marsh into this horizon to find tsunami sands. Purple means that tsunami sand was found. White means that no tsunami sand was found, and the thickness of the size of the circle represents the thickness of the deposit. So you get a sense of how the tsunami inundated at this site. So your mind as a modeler starts to go, I wonder what kinds of earthquakes you need to recreate not just the tsunami at that site, but the pattern of tsunami inundation at that site. And of course, another paleoseismic proxy is written accounts from people left behind in Cascadia. Well, this one, not in Cascadia, in Japan. This is why this earthquake famously became known as the orphan tsunami in the 2001 monograph put together by colleagues in the USGS and in Japan. This is a written account from the year 1700 that says in the Miyako district magistrate's office in Kuwagasaki village. We'll visit Kuwagasaki in a second. Here's the date and the past 8th day of night, hour of 9. That's how we know the date and time of the earthquake. A tsunami came. Here and there, the villages scampered to the hills. Afterwards, a fire started. 20 houses were burned. In addition, 13 houses were destroyed by the waves, and so on and so forth. So these accounts of a tsunami with no preceding earthquake shaking have been reported at not exactly, but close to the same time and the same day at these sites, very far away from each other in Japan. The distance from Kuwagasaki village all the way down here to Tanabe is more than 600 kilometers. So from that, we've backed out that the only likely source is a tsunami that started from an earthquake in the Cascadia subduction zone. So combine that with the widespread subsidence, the widespread tsunami evidence, the conclusion has been January 26th of 1700, a magnitude 9-ish earthquake had to have happened in Cascadia. There are the turbidites, and just to acknowledge that they're there, everywhere we look across the margin, Chris Goldfinger and many others throughout the years have been also collecting long piston cores on offshore marine with marine oceanographic vessels. And we see at each of these sites turbidites everywhere, evidence of usually at about 20 turbidites, Holocene turbidites in most of these cores. And again, the fact that they're up and down the margin has suggested that they have to be triggered by earthquakes, as opposed to any other kind of source that commonly triggers turbidites, like isopycnal flows or big storms or anything like that. They're very coherent across the margin, so we've associated them with large events. Now, you might well be asking yourself, okay, that's cool that the written account in Japan says January 26th of 1700. Does the dating, does the geochronology back that up? Now, not surprisingly, for those of you that know anything about carbon-14 dating, the radiocarbon dates are just not precise enough to place an event to the day, right? So if the details of this are unimportant, these are definitely the different dating estimates for different events, for different paleoseismic proxies across the margin. And all I want you to notice is that the sizes of these distributions are typically centuries. So if you look at a particular subsidence estimate or a particular tsunami deposit and you find like a little piece of wood or try to date a rhizome in a soil horizon or something like that, this is the best that you can do. So if we didn't have the January 26, 1700 date from written accounts, the best that we could say is something big happened in Cascadia 1700-ish, and put maybe a century either side of that date. The real geologic clue that has led people to believe that really it must have been January 26th of 1700 in accordance with what's written down in the Japanese accounts has been tree rings, dendrochronology. Now, for those of you, again, that know the history of Cascadia, this is nothing new. This is something you've heard before. But what surprised me when I started working on this is that the dendrochronology that says that there's cedar trees in coastal marshes that we know must have died between the winter-ish of 1699 and the spring of 1700, that very precise dating only exists for 7 red cedar trees at 4 sites spanning about 100 kilometers between central Washington and the Oregon-Washington border. I thought these trees were everywhere. I thought the evidence of these red cedar trees dying between 1699 and 1700 was everywhere across the margin, but it turns out that that's not true. It's only at those 4 sites in Washington. It's not because dendrochronologists don't try, it's because it's difficult. The right combination of factors has to be in place for you to be able to do this precise dating. I'm happy to talk more about that, though I'm also, there's many things I am not, and the dendrochronologist is one of them. Other attempts at dating things have been attempted from the turbidites themselves. There's something called turbidite fingerprinting or lithostratigraphic correlation, which is common in the oil industry, but which is taken and is put on steroids for Cascadia subduction zone problems. And this has been widely invoked to also say that the turbidites have to be synchronous. They have to all happen across the margin at the same time for the 1700 event. But there are many people, myself included, that think that those results can be debated. Happy to talk more about that. That's not an opinion that I'm alone with. But the point is that the dating alone does not favor or preclude all of the paleoseismic proxies, all of the subsidences, all of the tsunami deposits. The dating alone doesn't say that they all had to happen at the same time. So the fact that we think it's a single big rupture is, I think, based just on the dating up for debate. It could be part of the margin goes, and then 3 months later, another part of the margin goes. We see that in subduction zones across the world all the time. Sequences of ruptures spanning months, decades. So let's get into that. That's really what I want to talk about. If we revisit these paleoseismic proxies with modern geophysical modeling methods, what can we find? Okay, this is where it's going to get dense for about 8 to 9 minutes, but then we'll come back. So bear with me. How do we model? This is my side of the house. How do we model earthquakes? How do we model big ruptures? We need an efficient way to generate thousands of candidate ruptures. What we're doing is we're testing these ruptures against the geologic observations so we can rule them in or out. We can say that rupture, not likely. It really doesn't make the right subsidence. It really doesn't make the right tsunami. But we want to make thousands and thousands and thousands of them so we can explore everything that is possible. We use a technique called stochastic slip modeling. It's shown over there on the right. you're looking here at the total slip pattern when all is said and done. This is the amount of slip on the subduction zone interface. Here you're looking at the same thing, but you're looking at the propagation of the rupture and how fast the fault is sliding, the slip rate. Faults move at 0.5 meter per second or so. This is an open source code you can fiddle with. I'm going to give you just a few details about this. What's nice about this stochastic slip modeling code, which we call fake quakes, and I like to tell people that I came up with that name before Donald Trump announced his candidacy for the presidency. Otherwise, I would have never used the moniker fake anything because he has totally ruined that for everybody. But fake quakes is really fast. It's a reduced physics approximation. We're not modeling everything that we think we know about ruptures. It's a simplified method. And what stochastic slip means is that it makes the slip distribution on the fault at random. Now, randomness, that's what makes it fast. It's just a random number generator, if you want to think about it in its most simplest form. Now, that might sound to you a little weird that we're making random slip distributions on faults. But I want you to remember that random is not lack of structure. There's all kinds of random in the world. Probably you're most used to Gaussian white noise. When people say random, they usually mean Gaussian, with a standard deviation and a mean. And the standard deviation in a random process tells you how wild are the swings around the mean. But there's other kinds of random, just in time series. You could have something called random walk noise that is also random. It's unpredictable from one instant to the next, but it just kind of looks different. It has different structure and different properties to it, okay? So just because it's random doesn't mean that there's no rules or no structure to it. The same thing is true about this, that it happens for time series. The same thing is true in 2 dimensions. If I asked you to make a random number and distribute it on a 2-dimensional surface like a fault, depending on what statistics you pick, you're going to end up with things that look slightly different. Gaussian random would look like this, where black is more slip and white is less slip. But you could pick other random rules, like an exponential distribution, or there's a fancy thing called a fractal distribution, or a von Karman distribution. Point of the matter is that other people, long before me, figured out that when you look at slip on faults, it can be characterized as a random thing, best approximated by something called a von Karman correlation function. Details of this are unimportant. It's just a special kind of random. And so that's what we've put into fake quakes. You can press a button that says generate earthquake, and it will produce something that, like what's on the left, this is a random earthquake. And for those of you that maybe have been around seismology or earthquake geology for a while, that looks fine. That looks earthquakey based on what we know from looking at other big events, and yet it's a random thing imagined by the computer. Now, the other kind of random we've put into fake quakes is that when you ask the question, how long is a magnitude 8, or how wide is a magnitude 7, that's also kind of random. Magnitude 8s on average have a certain length, but sometimes they're longer, sometimes they're shorter. And so in fake quakes, we've also built in the ability, I'm sorry, that should be the next slide. We've also built in the ability to include that. So when you ask the code for a magnitude 8, it'll sometimes make it shorter, it'll sometimes make it longer. The other thing we've added, and which is really important, is that you can tell the computer, or you can tell fake quakes, to sort of precondition where it thinks that slip on the fault is more likely or less likely. And this will be important in a second. Here, for example, you can say, hey, slip should only be possible in the purple areas, because I just got to Cascadia and the powers that be have told me that earthquakes never extend offshore. So never extend onshore. So please make sure that when you create your random slip distributions, they obey that and they stay mostly offshore. So that's something that you can tell the code. Or you can say, I want the earthquakes to be possible deeper into the subduction zone and on land. So these 2 models are saying slip is equally likely everywhere in the purple region, and there should never be slip in any of the white regions. That's something you can do. Another thing you can do is you can be a little bit more delicate, and you can say, actually, from tectonic geodesy, from looking at GPS stations on land, we know that the fault, the megathrust, is highly coupled offshore, and that the coupling, how stuck the fault is, we know the coupling decreases as you come on shore. So I want you to use that information and leverage it. Make it so that when you make random earthquakes, they most frequently have high slip where we think the fault is coupled, and they have some slip, but less of it in the places where the fault is uncoupled. And that to me makes kind of sense. The fault is highly locked right now. That means that over centuries it's been accumulating a lot of slip. So in the next earthquake, there should be a lot of slip there. Now the problem is that we don't know exactly what the coupling looks like in Cascadia. We think it looks like this, but it could also look like this, or it could also look like this. And from the data we have, we actually can't tell those models apart. So rather than pick a side or decide which one of those coupling models is correct, we're just going to make ruptures with all of these assumptions. We're going to make 8,000 ruptures with this assumption, 8,000 ruptures with this assumption, 8,000 ruptures with this assumption, and so on, and then compare them to the geology and see who's the winner. So I got ahead of myself and I talked about the rupture length variability. We make ruptures that are sometimes long, sometimes short, totally at random. And so here's the summary of all of those choices that you can make in fake quakes. We use this von Karman correlation that tells you what kind of structure there is in the random slip of the fault. We use probabilistic scaling laws to make them short or long. We use these 5 different background mean models, the ones that say where slip is likely or not likely. And we generate a ton of ruptures in the magnitude range from 7.8 to 9.5. You can tell the code, I want ruptures in this magnitude range. When it's all said and done, we end up with just under 38,000 ruptures. And this plot just shows a summary of them. Each one of those gray dots is one of the models. That's a lot of complicated choices. And really, the way I want you to think about it is that these random rupture generators are like snowflakes. The rules, everybody knows that every snowflake is unique, right? That's something you hear as a kid. Even in tropical Mexico, we hear this. But the rules for making a snowflake are actually fairly simple. Complex behavior emerges from those simple rules. But depending on small, minute changes in the relative humidity when a snowflake was made, the temperature, how quickly it cooled, under what pressures it was formed, those can dictate the difference between a platy kind of snowflake and a dendritic kind of snowflake, but this is still just H2O crystallizing into the same system. So the same thing is at play here. These are my snowflakes. Depending on whether you choose this coupling model, whether you choose a long fault or a short fault and so on, you will arrive at slightly different looking ruptures that are all emergent from a set of simple rules. So for example, for a magnitude, if you pick a same magnitude, here is a magnitude 8.9 roughly, and it's short and stocky. Here is a magnitude 8.9 earthquake, and it's narrow and long. And the slip distributions are slightly different between them. Sometimes they will cover the entire plate boundary, like in this almost magnitude 9. Look at these two. They're the same magnitude, 8.9 and 8.9, but one has almost 45 meters of slip to the trench. One has never more than 15 meters of slip. I don't know which one is the right one for 1700, but let's test them all. So this isn't a new question. I'm not that smart. This is something that people have been asking since the very beginning when we rediscovered that Cascadia made earthquakes. The idea of whether 1700 was a single plate boundary event or a series of ruptures is something that was debated in the 80s and 90s as well. And they called it the difference between the dinner sausage model, a single plate boundary event, and the breakfast lynx model, a few events spanning years, decades in time. Now, most people would still maybe argue that the dinner sausage model is the right one because of the margin-wide distribution of the paleoseismic proxies, and because there is one previous effort from Kenji Satake and others back in 2003 that found that if you model the tsunami to Japan, these partial ruptures do not have enough oomph to get the right tsunami all the way to Japan. However, back when they did this in 2003, they used very simple earthquake sources, none of this detail of heterogeneous slip on the fault, concentrations of slip to the trench and so on, none of that was in this original 2003 modeling effort. So that's what we're going to do now. let's take these 40,000 snowflakes and check how they produce the subsidence and tsunami information in Japan. So I can model the subsidence. So for this event, this particular earthquake, this is just one random one. The coastal subsidence is the black line. And so the black line goes really well through these paleosubsidence estimates. And so what I'm going to do is I'm going to give ruptures grades of how well they fit the subsidence or not, but just based on what I'm calling their local subsidence, the subsidence of points around them. So in the case of this rupture, I'm not going to disqualify it because it doesn't fit the Northern California point, because that's just too far away from it. It's not reasonable to disqualify it for that. And so I'm going to keep low misfit ruptures, ruptures that match the subsidence really well to within 0.5 meter of RMS, which is about the uncertainty in the measurements usually. And then I'm going to model the ones that have really good subsidence. They make the right coastal subsidence in Japan. I'm going to model the tsunami propagation all the way to Japan. And from work by Atwater and others, we have reasonable estimates of the tsunami amplitude at these coastal sites in Japan from Tanabe, Miho, Nakaminato, Otsuchi, and Kuwagasaki. We could say, for example, at Kuwagasaki, between 2 and 4 meters is what we think the tsunami amplitude was there. So let's use that as well. So here's what that looks like. Out of the 38,000 or so ruptures, 1,600 of them have a really good fit to the coastal subsidence. So we throw away these gray ones. They just don't make the right subsidence. Off with their heads. And so we keep only these green ones. Of these green ones, we model their tsunami propagation to Japan, and that is what is shown down here. The shaded blue region is what Atwater and others think are the tsunami amplitudes in Japan. And so we see that events smaller than 8.5, these green violins, they never quite make the right tsunami. You really need something big. An 8.4 and 8.5 would never make the right tsunami in Japan. It's not until you get into the yellow, sort of pinkish and reddish ruptures, which are the 8.9s and largers, that you make the right tsunami amplitudes in Japan. So if we look at which events hit the right tsunami amplitude at every site in Japan, there are 93 of them. 93 out of those 1,600 events have the right subsidence in Cascadia and make the right tsunami in Japan. And their magnitude distribution is from 8.7 to 9.1, roughly. However, there's also an entire other family of ruptures, these ones right here. There's 529 earthquakes that make a tsunami smaller than 30 centimeters in Japan. This is where we think, for reasons that we can get into later, we're saying that anything smaller than 30 centimeters in Japan would never have made it into the written record of the Japanese archipelago. So there's 529 events that kind of fit their subsidence in Cascadia, but make a tsunami that's too small to have been recorded in Japan. And those go from 7.8-ish to 8.5-ish, 8.6-ish. So that gives us two families of ruptures that we can mix and match from to fill in the entire megathrust. Of the events that make the right tsunami in Japan, what we find is that they need to be predominantly in the south of the subduction zone. This is the centroid latitude. It's basically where the center of the slip model is in the subduction zone. If the event is in the south, more frequently than not, it makes the right tsunami in Japan. There's no events in the north of 47 degrees, very few events, so very few partial ruptures up here that would make the right tsunami in Japan. So if it's a partial rupture, it has to come from southern Cascadia. And there's lots of partial ruptures. These are the lengths of the ruptures. Events as short as 500, 400 kilometers can easily make the right tsunami in Japan. So let's mix and match from these two populations of earthquakes to see if we can make sequences of earthquakes. The rules are that only one event from the sequence can make the right tsunami in Japan. There's nothing in the Japanese records that say there were two tsunamis. There was only one tsunami. So there can be only one event that makes the right tsunami in Japan. And we can draw as many as 4 or more events that don't make a big tsunami in Japan, but that fit their local subsidence data. And then we're going to add all the subsidence signals. And the rule has to be that when you add all the events together, they still have to make the right subsidence signal in Cascadia, and we're not going to let the ruptures overlap, because we don't see that in real rupture sequences in earthquakes these days. We don't see a re-rupturing of a patch of fault that just ruptured. We don't see it rupture again 1 year later. And so here's an example of that for a one single event can still be invoked. So the traditional story that it was a plate boundary event from Northern California to Vancouver Island, that's still okay. That still works. But you could also have two events. This event outlined in blue, a 9.1, that makes the right tsunami in Japan and makes most of the subsidence signal. But then this 8.6 as a foreshock or as an aftershock fills in the rest of the subsidence signal and makes a tsunami that is too small to have been recorded in Japan. You can do it with 3, 4, and 5 earthquakes. If we pick, I don't know, maybe this n equals 4, this big blue event, magnitude 8.9, makes the right tsunami in Japan, fills in most of the subsidence signal, and then 2 little itty-bitty magnitude 8s fill in the subsidence signal offshore Vancouver Island, but don't make a big tsunami. And then 1 little itty-bitty magnitude 8.5 makes the rest of the subsidence signal in Northern California and Southern Oregon. That's perfectly allowable as well. And you can do it with 5 earthquakes too. I stopped at 5 because I think I made the point. And so when you look at the variability of sequences that you can make, of my 40,000 original snowflakes, there were 9, just 9, that are full plate boundary ruptures that still preserve the story. They make the right amount of subsidence, and they make the right tsunami in Japan. But if you go to 2 earthquakes, there are 20 magnitude 9-ish events and 182 events between 8.6 and magnitude 7.8, and you can combine these events in 271 different ways. You can make 271 sequences of 2 earthquakes and respect all the paleoseismology. You can make 66,000 sequences of 3 events and respect the paleoseismology. There's 91 big earthquakes and 400 odd smaller earthquakes that can be combined in different ways to make sequences of 3. You can make 140,000 sequences of 4 events. You can make 1.3 million sequences of 5 events. You get the idea. As you add more events, the complexity increases. So what we have learned from this exercise is that the conventional wisdom, if you want to call it that it has to be one single event, that's maybe still true. All of this is showing that in order to make the tsunami in Japan, you still need one really big earthquake, a main shock, if you want to call it that. It needs to be big, larger than 8.7. It still needs to happen on January 26th of 1700. So that's still true. But that big event, it doesn't even need to rupture by the location of these famous trees that died between the winter of 1699 and the spring of 1700. Those trees are right here in these yellow diamonds. For example, in this model, it's this event down here that makes the big tsunami in Japan. And it's really maybe an aftershock, an 8.2, that kills those famous trees, maybe 3 months, 6 months after the original event. What's really interesting here as well is that there can remain unbroken segments of the Cascadia megathrust. Frequently, offshore the Olympic Peninsula in northern Washington, we see sequences of ruptures where there are patches that haven't broken. And if that's true, what that means is that there's pieces of the Cascadia subduction zone that haven't had slip for at least 2 earthquake cycles, which is really bad news for earthquake hazards. Now, part of this gap exists because there's no paleoseismic constraint there. The environment for coastal marshes is not good there in the fast-rising Olympic Peninsula, so we actually have no paleoseismic proxies there, and that's why that gap is allowed there. So if I were a paleoseismologist, I'd figure out how to put some constraints there. Easier said than done. There can be many more magnitude smaller than 8 events in this building of earthquake sequences. I just ran out of computing power. After you get into the millions of possible sequences, you run out of computer memory. It is still possible that a single event explains everything, like in this case. I'm not saying that that's not true. Now, what we need to do going forward is get even fancier. I didn't tell you about the local tsunami. I spent a long time describing these tsunami deposits that are beautifully preserved in many sites, and I didn't say anything about their modeling, because that's what we're doing next. So this is that site that has a lot of cores where a tsunami is observed. And what we're doing now in collaboration with colleagues at the USGS, this is David Small's work, PhD student working with Jean-Paul Lassalle at the USGS, is we're playing the same game. We're modeling thousands of inundation runs at the different sites in Cascadia to see which kinds of earthquakes actually replicate what we're seeing in the geology. If you go to AGU, you can learn about this. Spoiler alert, it's really hard to make a magnitude 9 that inundates every single site correctly. We also need to figure out what to do with the turbidites, okay? The turbidites are still there. The problem is that it's really hard to connect my sources, my snowflakes, my earthquakes, connect them to the turbidites, because we have very cursory understanding of how you go from earthquake to shaking, from shaking to triggering turbidite, and from turbidite being triggered to transport down the canyon and eventual deposition. So looking at a core of turbidites and actually backing out what that says about ground motion and what that ground motion says about the earthquake that caused it, that is still hellishly complicated. But it seems like that's a worthwhile problem that we should try to tackle. So that's the story of that very first one. I told you I'd spent 97% of the talk there. So I won't bore you with number 2 a lot, but I will skip to the end here in a second. But this other idea that Cascadia earthquakes do not rupture inland is maybe even more impactful than this whole story of whether it is one or it is many. Impactful for you and me who live atop the subduction zone. We did the same thing. We tried thousands of ruptures and compared how they fit to the subsidence. And just to cut to the chase, because I want to talk about something else, here is the concluding slide. These are the kinds of ruptures where the slip stays offshore, and what I'm plotting there is the shaking predicted from those ruptures. So this is what I would say is what people who make hazard maps for the Cascadia subduction zone today, they would argue, well, no, it's not that they argue, this is the highest weighted kind of earthquake in our current hazard maps. And so I just want you to notice where the contours are 8, 7, 6, and 5. This is something that seismologists call modified Mercalli intensity. It's just a scale of how violent shaking is. And right around shaking intensity 5 to 6 is where the fact that we have so much unreinforced masonry in Portland and our cities is a real problem. At many subduction zones, buildings are typically built to withstand maybe MMI 7 and remain life safe. But in Eugene and Portland and Seattle and other places like that, we would see significant damage probably right around MMI 5. And you will see that all of our urban areas are well inside of that MMI 5 contour. So that's already pretty bad. It gets worse. If the slip is allowed to come on shore, these 3 kinds of shake maps are where the slip is allowed to come deeper into the subduction zone. If those are true, then these contours of shaking intensity start marching inland. And plotted here is the difference between these that have shaking onshore and this one that has shaking offshore. And wherever you see red, the shaking has gotten worse. And it gets significantly worse, especially for places like Eugene, which is bad for me. And here I've disaggregated how much worse it gets. Depending on what kind of model you pick, this is the one where the shaking is only offshore. Well, let's do Portland because we're in Portland. The expected shaking median intensity is 6. It could be way worse. Median is just the average. It could be way, way worse. If you let the slip come on shore, it starts to creep up into the MMI 7. And that seems like a small difference, but it's not. Between MMI 6 and MMI 7 is a little bit of damage and utter devastation. So understanding whether the slip can come on shore or not is really, really, really important for hazard assessments. And what we found is that these models where the slip is allowed to come on shore, they're still fine. They respect the coastal subsidence just fine. And so they're just as likely as the models where the slip is not allowed to come on shore. So long story short, we should also figure that out. And so what I want to finish with saying before I transition to my final 2 slides is that there's these 2 things that when I got to Eugene, people started telling me about the Cascadia subduction zone, that the 1700 event broke the entire plate boundary. What I would say to that is maybe, that still may be true, but also maybe not. There is still enough wiggle room in the observations to accept both views, and we should act accordingly. We shouldn't say that only one thing is possible and call it a day. The other one I was told is this issue that Cascadia earthquakes do not rupture inland. For that one, my personal view now is that that's most likely untrue. The fact that we have deep coupling from tectonic geodesy in the megathrust means that we cannot ignore the possibility that the slip can go deep into the subduction zone and the consequences for hazards are significant. Beyond having implications for interesting behaviors of the subduction zone, both of these deeply affect how we think about making hazard calculations for Cascadia. Which is why I'm posing this final challenge, and I would say that the geologists have done their job very well. The availability of paleoseismic proxies in Cascadia is really remarkable. This is probably the most well-documented subduction zone in terms of knowing its event chronology, compared to any other subduction zone in the world, short of maybe bits and pieces of Sumatra, where they have microcoral atolls that let you do that kind of stuff. But here we have the paleoseismic proxies all over. So now it's up to us, geophysicists, to respond and come up with ways of advancing our modeling strategies so that we can explore what kinds of behaviors are possible and allowable by the geology, so that we can use things like the tsunami deposits. Things that I think we should do is fake quakes that I told you about. I love it because I wrote the code. It's really simple, okay? It's not a full-fledged, full physics, what we would call a dynamic rupture model. It doesn't know about friction, doesn't know about stress. It's really dumb when you get right down to it. The reason we still use it is because more advanced dynamic rupture models, they take supercomputers and days or weeks to run a single model. So the idea of running 30,000 ruptures with a really nice dynamic rupture model, forget about it. We're nowhere near being able to do that. So things like GPU computing and machine learning to generate models and things like that are really things that we need to focus on. And all of this story was just about 1700. There's more events than 1700. The paleoseismic proxies allow us to peer at other events into the past beyond just the last event. So things like earthquake cycle models that model over many earthquake cycles, we should also do that and compare them against the paleoseismic proxies. And of course, understanding the turbidites seems like something we should really figure out because they're really valuable and they're also everywhere. And so I'll finish by saying this. This is because of this grand challenge of figuring out Cascadia. We started just last month something called the Cascadia Region Earthquake Science Center. Ashley here is deeply involved in that, maybe more deeply than you thought you would be involved. I'm sorry. This is a new NSF center that comprises the UO, but 13 other universities as well across the region and nationally. And we're supposed to do 3 things. We're supposed to do the science that looks at all of these problems, and many that I didn't talk about here today. But we're also supposed to connect the science to partners like Dogami and the USGS and FEMA and the resilience officer for the governor's office and tribal governments and other federal government agencies and so on, so that the science that we're producing is useful to them. And very importantly, we're also supposed to do, we're not supposed to, we're going to have a lot of programs in our geosciences education and inclusion arm that are about expanding access to geoscience education for primarily for minoritized populations. Because when I give talks like this, it's not frequently that there are many people that look like me in the rooms where I give talks like this. There should be, I don't know, there's maybe 30 of us here, I'm gonna guess. There should be at least 6 Latinos and Latinas in this room if we were a representative sample of the US. There should be about 3 to 4 Black people if we were a representative sample. Maybe 1 or 2 Native Americans, and so on. And so in the geosciences, we have a long, long, long way to go. And so we're trying to make a tiny dent in that problem through some of the geoscience education programs that we have at Crescent. And I'd love to talk to you more about that. Here's the distribution of institutions involved. In Crescent, it's a big, big collaborative effort because we have big, big problems, good problems. And so it involves PSU and UO, but also every other one of the usual suspects, along with some other hangers-on like Stanford, UCSD, Purdue, and some folks from the East Coast. That actually Virginia Tech is doing the most paleoseismology in this effort. So I think Tina Dura and Andrea Hawks, which were at Virginia Tech and UNC, they do all their work over here. I don't know how they made their decisions, but they should. They spend a lot of money on airplane tickets. And it Crescent funds a lot of students and a lot of faculty. Some of them are already identified, but others through the programs in our GEI arm. So we have a lot of funds for students that we haven't started funding because we haven't started recruiting. And we have money for about $30,000 of POP seed grants. So you can write a proposal, 2-page proposal that says, I know how I can contribute to Cascadia geoscience, either through education, through partnerships, or through a scientific activity. You write a 2-page proposal and we'll give you $30,000. The activities for each of those arms are listed here. I want to dwell a little bit on what's available for students. So for students, particularly at the undergraduate and graduate level, we have undergraduate year-long paid internships. So you're paid to do research the entire year. 9 months of the year, you do research at your home institution, wherever that is, PSU, for example. And then over the summer, 8 to 10 weeks, you get to go work at another university, the UO, for example. You can work with me or with someone else. And you get paid to do research over the summer somewhere else. So you would have 2 mentors, one at your home institution, one away. We have a course to code summer school, also for undergrads, where you get to go into the field to punch cores into a marsh and get subsidence estimates for 2 weeks. But then you get to do 2 weeks of learning how to use Jupyter notebooks and Python to make a tsunami model or a subsidence model, so that you can compare what you collected in the field with what you can produce from a model. We're going to have tons of technical short courses for graduate students. So say you're a graduate student in this department interested in learning about data science, ML, AI. There's going to be a technical short course for you. We're going to have travel grants for grads and postdocs. If you want to attend a workshop and you can't afford it through your university or department, you write a short fellowship application and we'll pay for you to go to a specific workshop. And so on. We're going to have a lot of educational cyber infrastructure. Anyway, I can talk more to you about it now if later. If you want to get in touch with us, that is me. I'm the one nominally in charge of steering this ship through this teeny tiny Suez Canal. My colleague Valerie Sahakian is in charge of connecting the science to our partners, to PG&E, to BC Hydro, to Washington DNR, and so on. If you have ideas, you can get in touch with her. Amanda Thomas, also at the UO, is running the science planning arm, and Andrew Meggs, who I think is well known to some of you here, is leading our geoscience education and inclusion arm. You can visit us at cascadiaquakes.org. All of what I told you now should hopefully be on the webpage. And if it's not and you have a question, you can always get in touch with me. And I'll stop there.